Welcome to Control 4 Driver Development Essentials. My name is Peter Kazenza. In this video, we'll look at how a device driver fits into Control 4's interoperability model. In the process of doing so, we'll define the architectural layers that enable a driver to successfully interact with not only a physical device, but the Control 4 operating system as well. As a driver developer, you are tasked with implementing this interaction. And successful driver developers build drivers that not only handle numerous dependencies placed on their driver code, but also seek out ways to enhance a device's capabilities in an automated environment. This level of interaction manifests itself as seamless device integration, a high level of device controllability, and ultimately, a quality end-user experience. After watching this video, you will have gained an understanding of the various operating system components that must be considered when designing a device driver. This is information that is referenced throughout all of the upcoming training modules. Grasping the information presented here will serve as a solid foundation for all of your driver development efforts. Let's get started. Like any other operating system environment, Control 4 has a few of its own unique language conventions and concepts. So, before we jump into reviewing driver code, let's take a minute and discuss some terminology that you'll be hearing quite often during this training series. Taking time now to review some of the more commonly used terms will make the remainder of this module, and subsequent ones, easier to understand. The first term I'd like to discuss is Director. Director is the software platform that runs on all Control 4 controllers. It communicates with device drivers in a manner that enforces a standardized API which hides the complexity of a huge array of different systems and protocols. It also uses that communication to serve up various user interfaces that are displayed on a wide variety of navigation devices. Next, we will discuss the proxy. This is a term that you will be hearing quite a bit. A proxy contains the definition for a specific class of device. Proxies are comprised of the most common examples of functionality for each device class. Proxies also provide a common interface that is delivered through the Control 4 Navigator UI. Proxies are predefined and supplied by Control 4. For example, one of the less complex proxies we offer is our light proxy. Let's take a look at the proxy documentation for lights in the DriverWorks Software Development Kit's Proxy and Protocol Guide. As you can see, the list consists of 16 intuitively named commands. This list is a representation of all of the Control 4 supported functions that a light manufacturer might include in their product. This set of commands defines the functionality of the light proxy and are included in the Control 4 light proxy driver. We'll explain how this light proxy driver is used by driver developers a little later in this module. Proxy drivers are supplied by Control 4 and cannot be edited. Shown is a quick overview of our current list of proxies. Now that you know what a proxy driver is, from a terminology standpoint, you're probably wondering how it's used. Control 4 provides proxies to serve as a layer that exists between Director and unique device drivers. Having a proxy for a class or group of devices simplifies the architecture around device control significantly. Consider a complex device class, such as audio-video receivers. The receiver proxy command list makes the light proxy look pretty simple. If we take a quick look at Control 4's online driver database, we'll find close to 50 receiver manufacturers, with one or more unique receiver drivers available for download. Now, imagine if every one of those receiver drivers had their own unique set of requirements needing to communicate with Director. If you consider the input commands alone across this amount of drivers, the variety and complexity of requirements is not insignificant. This is where a proxy comes into play. Specifically in our example, the receiver proxy. It provides a layer between Director and your device driver that offers a standardized set of commands that Director expects to receive, knows how to handle, and can respond to. In addition to this, a proxy provides a common user interface to control all receivers. As a driver developer, you'll be using DriverWorks API calls in your driver to communicate directly with the proxy layer. The proxy driver that is referenced in your device driver will then pass this information along to Director. Control4 offers proxies for a variety of devices. If you want to use one of the existing user interfaces displayed on Control4 Navigator devices, you'll need to select the proxy driver for your device type. These proxy drivers are already defined in the DriverWorks SDK. If you do not need to use one of the existing user interfaces, it is possible to create a device driver without a proxy driver component. If you choose to do this, your driver will still work within the Control4 system. However, the end user's interactions with the system will be limited to the Control4 programming elements that you, the driver developer, create through commands and events. This method could be used to implement functionality initiated by custom buttons or keypad presses. Now is a good time to talk about user interfaces. As I've mentioned, Control4 offers proxies for a variety of devices. If you want to use one of the existing user interfaces displayed on Control4 Navigator devices, you will need to select a proxy type that is already defined in the DriverWorks SDK. We refer to these user interfaces as Navigator UIs. Navigator UIs are interfaces that are graphically displayed on Navigator devices. These devices include TVs, touchscreens, remote controls, mobile devices, and so on. Another means of supporting user interaction and your device is the Programming UI. Programming UI refers to the interaction a user has with a device through program button presses, events, or other means that are configured in Composer Pro. The proxy driver provides for a standard set of programmable items here as well. So far, we've looked at Director and how it communicates with the proxy layer and Navigator devices. At this point, you should be wondering exactly how the device for which you are developing a driver comes into play. This is where we'll discuss the concept of the protocol. Remember when we discussed how a proxy is a representation of a class of device commands? Well, the protocol is similar, except for one major difference. It is device-specific. Simply put, protocols contain the definition for a specific device, and they are comprised of functionality that is unique to a specific device. Protocols are important as two similar devices may have the same functionality, but utilize a very different command syntax. Inside of your device driver, protocol code is written in XML and Lua, which is an embedded scripting language delivered with the DriverWorks SDK. The resulting file is referred to as the protocol driver. When we refer to a protocol driver, we're talking about the implementation of the protocol in the form of a driver file. Protocol drivers must have a .c4i file extension. When this driver is added to a Control4 automation system, device control is dictated by the functions defined in the protocol driver based upon the commands published by the device manufacturer. As we've discussed, Control4 Navigator UI is provided by the proxy driver, or proxies, which are referenced in the protocol. For example, a receiver protocol driver may use several proxies due to the features that the receiver supports. Now, let's take a look at the various user interfaces that can come into play with our receiver driver. The tuner proxy, which is used by our receiver driver, provides a standard UI, such as displaying the keypad which is used to enter station frequencies by the end user. The tuner proxy also provides us with standard programming elements that can be used to support user interaction. If we take a look at the programming for our tuner in Composer Pro, we'll find our proxy-defined commands here as well. We can also build user interaction through items such as button presses, events, or even create custom buttons in a project to help with control. At this point, we've talked about two distinct layers that deliver commands to control a device: the proxy and the protocol. A significant part of driver development involves handling feedback from a device once these commands are received. For example, when a user touches the light on icon on a touchscreen, the on command is sent to the light. The light then will notify the UI that the command was received and executed by delivering an on message, resulting in the light display changing on the UI. We call these messages proxy notifications. Proxy notifications are updates sent to the Control Force system that communicate status or update changes. Let's go back and look at our light proxy documentation. You'll notice that there is a defined set of proxy notifications already outlined. Control4 includes these as expected notifications that a light device will likely use. It is important to understand that this list is to provide a starting point to help with your driver development. It is certainly possible that your device driver may have notifications that are not defined in the SDK, and that's fine. We'll address how to handle these notifications that fall outside the defined list in an upcoming training module. Let's take a moment and review what we've discussed. First, we looked at Director and how it communicates with proxies through a standardized API. We also learned that Director can offer a graphical interface to a wide variety of Navigator devices. Then, we examined the role of the proxy and how it supports Director by delivering APIs that are easy for Director to consume. Finally, we talked about the protocol and how it provides unique, device-specific notifications that provide feedback from a device. Now, let's take a look at how data actually flows through these layers to support device control.